This panel is the most complicated panel in the entire model. That should be expected because geologic data is usually the most complicated data that goes into a model. Notice that if we look at any of the properties, we have several ways of entering the data. You can enter the data as a constant and enter one value for the entire model, or a constant by layer so that we have a constant value for each layer in the model, or we could bring in a map if we had map data. This is usually just for a full field model, not for a single well or a pattern model. Let's look at the depth data. If you follow along on your data sheet, you'll notice that the top of our reservoir is 8,870 feet deep. We will need depths for all of the layers in our model. Of course, we don't have these yet, so we'll have to determine what these are. So for now, let's just save this single value and go to the gross thickness data. We note from our data sheet that the gross thickness for our reservoir is 96 feet. We need to divide this in some logical fashion into our 7 layers. We also note that we've got a gas oil contact and a water oil contact, indicating that we have a gas cap, an oil zone, and an aquifer. Since we're modeling primarily an oil reservoir in this case, let's assume that the gas cap is the top layer in our model, the aquifer is the bottom layer, and the middle 5 layers will be our oil column. We see that the gas-oil contact is 8,900 feet, which is 30 feet below the top of the reservoir, so we'll put 30 feet as our top layer. Then we see that there are 50 feet between the gas-oil contact and the water-oil contact, so we'll take our 5 layers and make each one 10 feet. This accounts for 80 feet of our 96 feet gross thickness. That would indicate that the aquifer must be 16 feet. Save this. Let's go back to the depth. Now notice that since we have the gross thicknesses, we could determine what the depths for each of the layers would be. We could do this manually, or we could go up and ask Merlin to calculate the structure from gross, and it would set up our depths for us. Enter our net thickness, and we note that the net thickness is not given, but we do have a net to gross ratio of 0.73. So we'll enter the 0.73 in the net thickness area and specify that we're using the net thickness in the net data. Save this. Now let's go back to the net and set it to by layer and calculate the actual net thicknesses in each layer. Since we have the net thickness as a net to gross ratio, we can go up and calculate the net as being equal to net to gross times gross, and we will see the net thicknesses for each layer. Now we'll enter the porosity data, and we note that our porosity is 30% for the entire reservoir. So we'll enter 30, fill the area with this value, and save this, and we get a warning message. Merlin has extensive warning messages to warn you when you've entered data that may not be quite right. For this case, it says that porosity in layer 1 seems over large. Normally it's not over 1. Do you want to save this data? No, let's cancel it. If we look at porosity, we note that the porosity should have been entered as a fraction instead of a percent. Well, that's easily correctable. We'll select the values we have entered and perform mathematics and divide by a constant of 100. That will convert our percent into a fraction, and save this. Finally, we'll enter permeability. Merlin can handle heterogeneous permeability or directional permeability. If we enter the Kx, we will just enter both values as being the same, and we note that the permeability is 234 millidarcies. So we'll enter both Kx and Ky as being the same value. And we'll enter them as being a constant for the entire model rather than by layer. Kz, the vertical permeability, is not given, so we'll have to use our engineering experience. And generally we assume that KZ is probably 10% of the horizontal. For your reservoir, you may want to use a different fraction. In our case, we'll just use 10%. So we would enter the KZ of 23 millidarcies. This really is all of the geologic data. It seems very simple for a single well model where everything is pretty much homogeneous, but for a full field model where we're bringing maps in, we would have many more tools available to us that we could use to enter this data. This concludes the entering of the geologic data.